Hello everyone, welcome to the lecture series on deep learning. The first and the foundation of a deep learning is depends on the linear algebra that forms the mathematical foundation of a deep learning. Every neural network, regardless of its complexity, is built using four basic mathematical objects, which includes scalars, vectors, matrices, and tensors. In this session, we will understand these concepts and see how they are used in deep neural networks. In today's lecture, we will discuss about why linear algebra is important for deep learning and the scalars, vectors, matrices, tensors, how these mathematical objects flow through a neural network. By the end of this session, you will understand the building blocks behind every deep learning model. Before learning neural networks, let us understand why linear algebra is important. Deep learning models do not work directly with images, text or audio. Instead, all types of data are first converted into numbers. Say for example, a color image is represented as pixel values, a sentence is converted into numerical words embeddings, audio is represented as a sequence of numerical samples. Every layer of neural network performs mathematical operations on these numbers. One of the most important equation in deep learning is y equal to wx plus b, where x represents the input, w is the weight matrix, b is the bias term, and y is the output value. This operation is repeated across multiple layers until the model produces its final prediction. Another reason for linear algebra is important is that GPU are specifically designed to perform matrix and tensor operations efficiently, making deep learning much faster. Let us begin with the simplest mathematical object, the scalar. A scalar is simply a single numerical value. It has no direction and no dimension. So it is called a rank 0 tensor. The examples include the learning rate used during model training, the last value which measures prediction error, a bias term added to a neuron, a single weight within a neural network. Although a scalar contains only one value, it plays a crucial role in controlling the learning process. Next, we have the vectors. A vector is an ordered list of numbers, making it a one-dimensional array or rank 1 tensor. The diagram shows the one-dimensional array of numbers. In deep learning, vectors are used in many forms. A feature vector represents the input data. A word embedding represents the meaning of a word as a numerical vector. A weight vector stores the parameters of a neuron. A gradient vector tells us how to update the weights during training. Vectors are therefore fundamental for representing both data and model parameters. Several important mathematical operations can be performed on vectors. The first is vector addition, where corresponding elements are added together. The second is a scalar multiplication, where every element of a vector is multiplied by the same scalar value. This operation is commonly used when applying the learning rate during gradient descent. The third and most important operation is the dot product. The dot product multiplies corresponding elements and sums the results into single number. In deep learning, every neuron computes its output using the dot product between the input vector and the weight vector. Finally, we have the norm, which measures the length or magnitude of a vector. Vector norms are commonly used in regularization techniques to prevent overfitting. Now let us move to matrices. A matrix is a two-dimensional arrangement of numbers consisting of rows and columns. It is called a rank 2 tensor. Matrices are represented using uppercase letters such as W and A. Examples in deep learning include weight matrices connecting one layer to the next, a batch of training samples, grayscale images where each pixel occupies one position in the matrix, attention score matrices used in transformer model. Matrices allow neural networks to process many values simultaneously rather than one at a time. Matrix multiplication is one of the most important operations in deep learning. Suppose we have a weight matrix W with the dimensions 4 by 3 and an input vector X with the dimensions 3 by 1. When we multiply them, the output becomes a vector of dimensions 4 by 1. One important rule is that the inner dimensions must match. For example, A matrix of a size m cross n can only be multiplied with another matrix of size n cross p. Another important concept is the transpose, represented by W superscript of T, which exchanges rows and columns. Also remember that matrix multiplication is not commutative. That means AB is generally not equal to BA. Every fully connected layer in a neural network uses the equation y equal to wx plus b to transform input features into output features. The most general mathematical object used in deep learning is the tensor. A tensor is simply an n-dimensional array. In fact, a scalar is a rank 0 tensor, a vector is a rank 1 tensor, a matrix is a rank 2 tensor. Anything with 3 or more dimensions is called a tensor. A color image with dimensions like height with and width multiplied by the channels is a rank 3 tensor. A batch of images adds another dimensions and becomes a rank 4 tensor. Similarly, videos and transformer activations are also represented using tensors. Modern deep learning frameworks such as TensorFlow and PyTorch perform almost all computations using tensors. This table summarizes everything we have learned. A scalar contains one value, a vector is a one-dimensional array, matrix is a two-dimensional array, a tensor is a multi-dimensional array. The higher the rank, the more complex the data representation becomes. Understanding these mathematical objects is essential before learning neural network architecture. Let us see how data flows through a neural network. Suppose we start with the input image of size 224 by 224 with the 3 color channels. After passing through a convolutional layer, the image is transformed into 32 feature maps. Next, the feature maps are flattened into a long vector. This vector is then passed to a dense layer, where matrix multiplication extracts the most important feature. Finally, the output layer produces class probabilities for prediction. This example shows that every stage of a neural network involves tensor operations such as reshaping, convolution, and matrix multiplication. Let us summarize today's lecture. We learned that all deep learning models are built using 4 mathematical objects: scalars, vectors, matrices, and tensors. The shape of these objects determines how mathematical operations can be performed. Among all operations, matrix multiplication is the most important because every dense neural network layer depends on it. Finally, deep learning combines linear algebra with nonlinear activation function to learn complex patterns from data. Thank you for watching.